All right, anyone explain to me what's happening to number two?
Or like the negatives, they're moving back to their original position.
Moving back to the original position, okay. Then what happens?
And then like the bottom two sticks, like they come together.
Okay, yeah, that's exactly what's happening. Can anyone describe to me the charges? What's happening with the charges? There's more things that are going on in the video. While Samarja is correct, there's not, that doesn't describe everything that's happening in the video. You gonna leave soon? Yeah, sure.
The charge is like neutral because like there's like one negative for each positive.
Well, the whole entire thing was neutral in the first place. But you're right, like the bottom is now neutral. So let's talk about this. Let's describe this thing in full. So you bring a positively charged rod near a sphere, the electrons gather at the top. But then what happens at the top is that the top is now negatively charged. Right? That's what it's saying. And the bottom is positively charged. Now, after you move, after rod is removed, it goes back to being neutral, right? The electrons move back. But now the metal leaves are neutrally charged, are now neutral. So they do not, so they don't attract or repel. So they don't attract or repel anymore. Right? That's what you should see. That's what you should be seeing. Does it make sense, guys? We all doing this? This is number two. I'll give you 1 to 2 minutes. I'll give you 1 to 2 minutes and then we'll move on. All right, let's go. Let's go. Let's go. Now, this next video that I'm going to show you is extremely, extremely, extremely old. I would say it's around 20 years old. But it's a very good video despite all its faults. Right? The video, the quality might be bad. It might be like 240p. The audio quality might be horrible. But despite both of these faults, it is extremely, extremely good at showing you electrostatic induction.
way to acquire an electrostatic charge is to come in close contact with another object that consists of different material. Cotton, for example, has greater attraction for electrons than wool. Therefore, when these materials come in close contact with each other, electrons transfer from wool to cotton. The cotton now has an overall negative charge, and the wool an overall positive charge. Their opposite charges account for the static cling when you attempt to separate them. The easiest way to neutralize a charged object is to connect it to the earth with a good conductor called a ground. If the object is negatively charged, the excess electrons flow into the ground until it is neutral. If it is positively charged, electrons flow from the ground into the object until once again it is neutralized. Close contact between two neutral objects is not the only way to acquire an electrostatic charge. If a neutral object is touched by a charged one, there will be a transfer of charge as electrons flow from the charged object to the neutral one. And how do we detect charge? A metal leaf electroscope does not make contact. What is evidence that the electroscope is charged? The process of positive electroscope, when approached by a charge rod, seems to anticipate what is about to happen. The leaves diverge even though the rod does not make contact. If the rod is removed, the leaves collapse again. What's going on here? Well, let's apply some of the theory we've learned so far. We can visualize the electrical condition of the rod and the electroscope by showing a representative sample of the charges. Since the electroscope is metal, electrons can move with relative ease within it.
Yeah, Ray started recording.
If, as a result of their
I have
random
find out
motion,
your doctor's appointment.
some electrons come close to each other, the repulsive forces that they exert on each other ensure that they will very quickly move apart again.
Bye-bye.
When a positively charged rod moves towards the knob, the charges interact. The electrons in the electroscope will try to move towards the rod. And as they do so, will flow out of the metal leaves, making the leaves positive. As a result, the leaves repel each other and diverge. When the electrons in the electroscope move towards the rod, they get closer to each other and repel each other more strongly. So, for each electron on the knob, the attractive force of the positively charged rod is balanced, both by the repulsive force of the other electrons near it and the attraction of the positively charged leaves. If we look at the electroscope as a whole, we find that the top is negatively charged and the bottom is positively charged. Since no charge has been transferred, the electroscope as a whole is still neutral. It has, however, experienced induced charge separation. If the positively charged rod is removed, the electrons will no longer remain concentrated in the knob, but spread out uniformly throughout the electroscope. As a result, the electroscope no longer has induced separation. Let's bring the rod close to the electroscope again. This time we'll ground the electroscope while the positively charged rod is held.
We're not gonna watch that part. That's not important because you guys won't ever be tested on it. Anyway, hopefully that was a good visualization, right? Hopefully. I think it was like I told you, despite all the how old the video was, I felt like it was like the best video to show you regarding electrostatic induction. I really do think so. All right, let's do problem number 3. Two metal spheres A and B are on insulating stands. And so sphere A possesses an excess of electrons, so it has more as negatively charged. Right, it's negatively charged. And sphere B is neutral, so sphere B is neutral. What do you think happens if you bring a negatively charged sphere, sphere A, next to sphere B? What's going to happen? What's the charge distribution going to look like?
I think the electrons from sphere A are going to transfer over to B.
Well, they're not going to touch. They're not touching. They're not touching. They're never going to touch, so they can't transfer over. What do you think this negatively charged sphere is going to do to the electrons in sphere B? What do you think happened? I mean, it's the same concept as the electroscope. It's the opposite. Letting me down, guys. Come on. Yeah, it's going to repel. The electrons in sphere A is going to repel the electrons in sphere B. So which way are the electrons in sphere B going to move? Are the electrons in sphere B going to move to the left, to the right?
They're going to move to the right.
Yeah, so the electrons on sphere B, they don't want to get anywhere near this negatively charged sphere. They're going to move all the way to the right. Right? They want to get away from the negatively charged sphere. So you're going to have more electrons on the right. They're all going to move to the right. Any questions about that, guys? Please let me know. Give me time to copy this down, guys. I'm going to give you like 1 or 2 more minutes. I drew it. So the question was asked you, what does the charge distribution look like? So where exactly are the electrons and the protons? Now, sphere B is neutrally charged. Sphere B is neutrally charged. One more electron. Now, if you were to bring a negatively charged sphere next to sphere B, what's going to happen is that, well, the electrons are going to be repelled by the negatively charged sphere. So what's going to happen is that the electrons are now going to move to the right-hand side. And so this is what it would look like. This would be the charge distribution. This is what charge distribution means. A very good example of that is on the lesson on Friday. Is this. It's the same thing that's happening in this GIF. And you bring a negatively charged object near a neutral sphere, what happens is that the electrons move to the right-hand side, move to the other side. I don't know about you guys, but when I'm visualizing this, I'm visualizing that like there's like an invisible force for me personally. I visualize that there's like this entire, well, it is a force, right? I visualize there's like this entire force surrounding my negatively charged sphere. And it's basically pushing away all other electrons. That's how I visualize things. I don't know how you visualize things, but that's how I visualize it. Some of you guys haven't even gotten started on your Go formative. Again, guys, you get classwork participation grade off for this. All right, let's move on. Number 4. So you have 3 spheres, which means they're all touching, right? Which means that charges can move between each other. But they're all positive. I mean, they're all neutral. So each of these 3 spheres are neutral. What is the charge distribution gonna look like? What are my charges gonna look like if I bring a positively charged rod near sphere X? What does a positively charged rod do?
Like the positives, they're gonna move to the right side of the sphere.
Protons are never the one that's moving.
Oh, so the electrons might move to the left?
Yeah, the positively charged rods are attracting the electrons, guys. The protons are never the one that moves. Please remember this. Protons aren't the one that's moving. So what happens when you bring the positively charged rod near the sphere X? Well, all the electrons are now going to move to the left-hand side because they are attracted now. They're attracted. Are there any questions? So this is what it looks like for number 4 looks like. Now,
Can
you
you
get
go back
4,
to
but you
3 real quick?
say that again?
Can you go back to number 3 real quick?
Yeah, sure. You get 4, but you still don't get 3. Huh. Do
I'm sort of
you?
confused. I'm sort of confused on what they mean by neutral. By neutral, do they mean that like there's both
Neutral
positive
means
and negative
equal
in
amount
it?
of protons and
So
neutrons and electrons.
so neutral means it has both of them inside, but they're even. Is
Yes.
that what you mean?
Yes.
So basically, three is saying A has an excess amount of neutrals and B has both protons and neutrals, but they're equal to each other,
Both
right?
protons and electrons. Yes.
Okay.
So that's what positively charged objects still have electrons, guys. But positively charged objects just have more protons than electrons. That's really the only requirement to being positively charged. This is positively charged. You have more protons than electrons. Now, number 3 is basically this gift right here. If you bring a negatively charged object near a neutrally charged object, what happens is that the electrons in a neutral object, they move to the right-hand side. They move away from the negative charge because they are repelling each other. Negative charges repel negative charges. Question 3 is the same concept as question 4, but just the opposite, because question 4 is this. Question 4 is like, if you bring a positively charged rod near a neutrally charged object, the electrons are going to be attracted and they move close to the rod. Number 3 is the opposite. You bring a negatively charged rod near a sphere and they repel electrons and the electrons move to the other side. So again, it's like, well, you have sphere B is negative. Sphere A is negative. Sphere A has more electrons than protons, whereas sphere B has an equal amount of protons and electrons. But what happens is that because sphere A is negative, it's going to repel the electrons in sphere B. So the electrons are going to go to the other side. You have to tell me specifically what you don't get, so I can help you more efficiently.
Who, me?
No, someone messaged me privately. Anyway, guys, if you did 3 and 4, make sure you submit the assignment, and there is homework, but the homework is based on a lesson. Pretend the rod is sphere A. Pretend the rod is sphere A. Pretend it is sphere A. It's basically an object. It doesn't need to be a rod, it can be any object. You missed number 4? I'll just put it up. Anyway, guys, you can go if you didn't realize it yet.
Should we submit when we're done?
Yeah, submit it when you're done.
Okay.
Guys, I'm going to turn this off now. See you guys on tomorrow.